Hello. In this video, I'd like to talk a little bit about pi. No, not that kind of pi. The number pi. 3.14 and so on. I've sometimes heard people say, or seen people write, like on the internet, something like pi is a very special number because it's infinite. Now, is that true or false? Well, in this video, I'm going to give you my answer. First of all, pi is a very special number. True or false? Well, that part, I think it's true. Pi is the ratio of the circumference of a circle to its diameter. So that means you can take any circle of any size, no matter how big or how small, as long as it's a perfect circle, and divide the distance all the way around by the distance all the way across, and the result is always going to be the same number. And we call that number pi, and we use the Greek letter pi as the symbol to stand for that particular number. And that number comes up in other formulas, like the formula for the area of a circle or for the volume of a sphere. And it also comes up in all sorts of other situations that you wouldn't think have anything to do with circles, but it comes up in different areas in math. So I think it is safe to say that yes, pi is a very special number. Well, is pi infinite? Well, that kind of depends on what you mean, what you're trying to say when you say pi is infinite. Now, normally, when you say something's infinite, you're talking about how big it is. And pi, well, it really isn't all that large. It's only a little bit more than 3. It's between 3 and 4. So it's not a very big number. It's certainly not an infinitely large number. So I would never say pi is infinite. But what I might say is pi has infinitely many digits, or pi has an infinite decimal expansion. Or if you try to write pi out in decimal form, the digits just keep on going forever. There are infinitely many digits after the decimal point. And that is true. The value of pi, well, you can't write it exactly because the digits just keep on going forever. But it starts out 3.14159, and then it just keeps on going from there. So the digits keep on going forever. You can never stop writing and say, there, that's the exact value of that number pi. Now at this point, a couple questions might occur to you, like, how do we know that pi has infinitely many digits? And how do we know what those digits are? Well, I'm not going to answer those questions right now, but I will come back and say a little bit more about them before the end of the video. But now let me address the claim that pi is a very special number because it has infinitely many digits. And this, I think, is false. It's true that pi is a special number. It's true that pi has infinitely many digits. But I don't think it's fair to say that pi is a special number because it has infinitely many digits. That would be a little like saying the Pope is a very special person because he has 5 fingers on each hand. Well, it's true that the Pope is a special person. It's true that the Pope has 5 fingers on each hand, but that's not why the Pope is a special person. He's not special because he has 5 fingers on each hand. There are lots of people who have 5 fingers on each hand. And there are lots of numbers that have infinitely many digits. Although they're not usually the numbers you first think about when you're thinking about or learning about numbers. The numbers you usually think about and are used to using and encountering every day are things like the counting numbers, 1, 2, 3, and so on. So a fairer analogy might be to say, well, it isn't all that special being Asian. There are lots of people who are Asian. More than half the world's population is Asian. But if you grew up in a small town in, say, Africa or Scandinavia, and somebody moved to your town from Asia, you might think they were pretty special because they were from Asia. Oh, that's the Asian guy. So pi, it's certainly not unique in having infinitely many digits. There are lots of numbers like that. But they're maybe not the numbers that you usually think of when you think of numbers. But let's look at some other numbers that have infinitely many digits. Take the number 1/3. In decimal form, the fraction 1/3 would be 0.33333, and the threes just keep on going forever. Infinitely many digits. They're all threes, but there are infinitely many of them. The number 2/7 in decimal form goes 0.285714, 285714, 285714, and so on. And that 285714 just keeps repeating over and over and over again. The number 1 and 1/22, which could also be written as 23/22, in decimal form is 1.0454554545, and then it just keeps on going like that forever. The 4/5 part just keeps repeating. Now these numbers do have infinitely many digits after the decimal point, but they're somewhat different from pi in that they are repeating decimals. These are all examples of what we call rational numbers, and they're called that because they can be written as a ratio. One integer or whole number over another, like 1/3 or 2/7 or 23/22. And in decimal form, a rational number will either just terminate, like for example 1/4 is 0.25 and that's it, or it will repeat. It will repeat the same digit or same string of digits over and over again, like the examples we see here. Now that first thing is true by definition. That's what it means to be a rational number. It means you can write it as an integer over another integer. And then it can be proved, it's not too hard to show, that if you have a number that can be written as something over something else, an integer over another integer, then when you write it in decimal form, it will either terminate or repeat. You'll get a repeating decimal. Then the numbers that are not rational numbers, there are other real numbers that are irrational numbers. So those are the ones that cannot be written as a ratio of integers. And if you try to write those in decimal form, they will not terminate and they will not repeat. They will go on forever without repeating. And so pi is an example, a famous example of an irrational number. It cannot be written exactly as one whole number over another. And if you try to write it in decimal form, the digits just keep on going forever, and they don't just repeat the same pattern over and over and over again. You never know what you're going to get. I mean, I put a ... at the end here to show that the digits keep on going, but there's no obvious pattern to them. You can't tell by what I've written already what the rest of the digits are going to look like. But there are other irrational numbers besides pi. Another famous irrational number is the one we use the letter e to symbolize. This is the base of the natural logarithm function. It comes up when you're dealing with things like exponential growth. So this is another famous irrational number that shows up a lot in math. And then there's the square root of 2. That is the positive number that when you multiply it by itself, you end up with 2. This might have been the first irrational number ever to be discovered. The first number that people were able to figure out that it was irrational. So the square root of 2, you can't write down exactly what that number is. It starts out as 1.414, and then it goes on from there. But if you stop writing digits, then what you have is a number that, when you multiply it by itself, is close to 2, but not exactly 2. If you want the exact square root of 2 in decimal form, the digits just keep on going forever. And it's not just the square root of 2, that's true of the square root of anything that isn't a perfect square. Like, for example, the square root of 14 is irrational. Also, the cube root of something that isn't a perfect cube would be irrational, or the fourth root of something that isn't a perfect fourth power. So these are all irrational, and then there are other irrational numbers that are related to these, like because pi is irrational, so is 2 pi, or pi over 6, or pi plus 0.007. And then there are a lot of irrational numbers out there that don't really have anything special about them and that you may never encounter or even know how to talk about. Now, getting back to those two questions that I said I'd say a little more about earlier. How do we know that pi has infinitely many digits? That is, how do we know that pi is an irrational number? Can we prove that? Well, for a long time we couldn't, but in 1761, someone finally managed to prove that pi is, in fact, an irrational number. And this was not easy to do. By contrast, the ancient Greeks, way back well over 2,000 years ago, were able to prove that the square root of 2 is irrational. So it's fairly easy to show that the square root of 2 is an irrational number, but it's not so easy to show that pi is irrational. It can be done. I'm not going to explain that in this video. That goes way beyond the scope of this video, and it gets into some fairly advanced math, but it's something that you can look up on the internet and see how people have managed to prove that pi is an irrational number. And how do we know what those digits are? Like, do we draw a big circle and measure its circumference and measure its diameter and divide to get the value of pi? Well, no. You're never going to be able to draw a circle precisely enough or measure it accurately enough to get more than a very rough approximation to just a couple digits of what pi is. Rather, there are formulas that can be used to calculate pi to as many digits as we need. And so those formulas, or those mathematical techniques, and again, this is something that I'm not going to explain in this video, but you can look up online if you want to know more. There are formulas that can be used to calculate pi to as many digits as we need. Then another question that comes up is, okay, so if the digits of pi go on forever, does that mean that every possible whole number or every possible finite sequence of digits must appear somewhere in that infinite string of digits that make up the digits of pi? Like, if you go out far enough in the digits of pi, are you guaranteed to find your phone number or the serial number of the computer that I'm using to make this video? And, well, the answer is we don't know for sure, but it takes more than just infinitely many digits to guarantee that that will happen. So just because the digits go on forever, that's not enough to guarantee that we'll eventually find anything that we might be looking for. I mean, after all, we've seen that the decimal form of 1/3 has infinitely many digits, but you're not going to find your phone number there unless your phone number is made up of all threes. So there's an example of a number with infinitely many digits, but that does not contain all possible strings of digits. And it's not enough for pi to be irrational. What if I took all the digits of pi, but then I replace every 8 with a 7? So the number that is made up of all the same digits as pi itself, except that everywhere pi has an 8, this number has a 7. It still goes on forever. It is still irrational, but it does not contain every possible number or sequence of digits. If your phone number has any 8s in it, you're never going to find it here. So that rules out this number, but what about pi itself? Well, if pi is what's called a normal number, that would mean that it does indeed contain every possible finite sequence of digits. So if this is something you want to learn more about, Google normal numbers. Now, actually, the word normal means a bunch of different things depending on the context. It has different meanings in different areas of math. You can talk about normal distributions in statistics or normal subgroups in abstract algebra, things like that. But here we're talking about a normal number being a number where all the digits in its infinite decimal expansion show up with the same frequency. And all pairs of digits are equally common, and all triples and all quadruples, and every finite sequence of digits will eventually show up as often as every other finite sequence of digits of the same length. So if this is true of pi, that would mean that every whole number or every finite sequence of digits is guaranteed to exist somewhere in that infinite decimal expansion. Now, we don't know for sure whether this is true. It might be, but we haven't been able to prove or disprove for sure. It's a hard thing to prove. So it's likely that this is true of pi, and it's also likely that it's true of other famous irrational numbers like e or the square root of 2, but we don't know for sure. But if it is true, that means that somewhere out in the digits of pi, there is your phone number, and there is the serial number of the computer that I'm using, and there is the complete works of William Shakespeare translated into decimal digits. Now, just because it's in there somewhere doesn't mean that we know where it is. It's probably not in the 100 trillion or so digits of pi that human beings, with the help of computers, have been able to calculate so far. We've been able to calculate maybe 100 trillion digits, but there's still infinitely many after that we haven't gotten to yet. So if you go looking for your phone number in the digits of pi, it might be there somewhere, but that doesn't mean that you're going to find it before you die of old age.